I made up a new set of data, and instead of it being instead of it being high school GPAs, it's now college GPAs. We still have a population of 10 people and a sample of 9 people over here, and the numbers aren't exactly the same as they were last time, but I made it so that they would still add up to 20, and then 20 divided by 10 is 2. I also made it so that the, the 9 numbers would add up to 18, and then 18 divided by 9 is 2. So on purpose, I made it so that the population mean and the sample mean would come out to the same number. That wouldn't usually happen. And if the sample mean came out to a different number, like 1.5, we would have to subtract all of these by 1.5. I've already done all of this work for you before I even started the video, so now we can just go straight to finding the values. Let's add the absolute deviations for the entire population. They added up to 7, and then 7 divided by 10 is 0.7. Let's do this. Let's also find the mean of the squared deviations, which will be our population variance. It equals 9. We divide by 10 since we have 10 squared deviations, and we get 0.9. That's our population variance. Population standard deviation is just whatever the square root of the population variance equals. Comes out to about 0.95 this time. About 0.95. The variance, standard deviation, and mean absolute deviation actually always come out to positive numbers. Now, what about the sample? We can find the mean of the 9 absolute deviations in this column right here, and that would be the mean absolute deviation of the sample. Comes out to 7. 7 divided by 9, since we have 9 numbers, is 0.78. Remember, the mean absolute deviation isn't adjusted for the sample. It's calculated the same way regardless of whether it's a population or a sample. So it equals about 0.78. What about the sample variance? We just have to add these squared deviations and we have to actually calculate an adjusted mean or an adjusted average in which we divide by one less than the number of numbers, which is it'll be 8 instead of 9. So let's add the squared deviations. It equals 9. But remember, we have to divide by 8 because we're doing a sample variance and not a population variance. We get 1.125. And then whatever the square root of the sample variance equals is what the sample standard deviation will be. The square root is 1.06. Notice how the standard deviation and the mean absolute deviation come out to about the same number. So they're pretty much about showing the same thing. The variance usually almost always comes out bigger than both of them. Except if the variance is a decimal like 0.9, the square root will actually be a larger number, so the standard deviation comes out to 0.95. But if it's not a decimal, if it's a number above 1, then the standard deviation will come out smaller than the variance. And you might be wondering why the variance and standard deviation are adjusted when it's a sample, but the mean absolute deviation isn't adjusted. No adjustment has been developed for the mean absolute deviation because it's pretty much never really used in actual data collection, but the variance and standard deviation are used. So they actually have developed an adjustment for variance and standard deviation for when the data comes from a sample. And the purpose of that adjustment is to make the sample variance and sample standard deviation come out to larger numbers than they would otherwise. When you divide by one less than the number of numbers, you get a bigger answer for the variance, and then the standard deviation also comes out larger. Because when you take the square root of a larger number, you get a larger number. And it's meant to help prevent the sample variance from underestimating the population variance, and it's meant to help prevent the sample standard deviation from underestimating the population standard deviation. There's a tendency for the values, for the dispersion values that are calculated with the sample, to underestimate the dispersion values that are calculated from an entire population. And this just helps adjust them so it brings them up closer so that they better estimate the population values. And I said that it helps prevent it from underestimating, but what I should actually say is that it helps adjust for, there's actually a tendency for these to underestimate the population values. Meaning, if you took a lot of different samples from the same population and calculated these values with each of those samples, there would be a tendency for more of those samples to underestimate the values for the entire population, and fewer of them to overestimate. So it helps correct for this tendency for samples to underestimate the population variance and population standard deviation.